We started chapter 5 today. So the title of this chapter is Patterns Leading to Addition and Subtraction, and the essential question of the chapter is, how are addition and subtraction applied and connected to algebra, geometry, probability, and statistics? So as we go through chapter 5, you want to always keep that big idea in mind. How are we connecting the ideas of addition and subtraction? How are we using them in algebra, geometry, probability, and statistics? So we started off reviewing what you knew in grade 1 about, excuse me, I can't get this to clear. Anyway, when you were in first grade and learning to add or subtract, what was the meaning of addition? And the meaning of addition had to do with, I can't get the, oh, there we go. Almost every class came up with it. You learned to put things together and to count them. And this is the same model we're going to use today for algebra and geometry, the putting together model. And for integers, we're going to use the slide model. And this is where you're sliding along a number line to show addition, or to show adding a positive number or adding a negative number. So we used your slates today to practice. So whether it's decimals, percents, fractions, mixed numbers, integer, etc., we use addition for the putting together model. So it's just putting groups of things together. So we started off with the algebra expression x plus y, which just means I'm going to put together something that is represented by x and something represented by y to get the total of x plus y when I put them together. And I can always do that as long as there's no overlap. And I thought the best way for you to figure out what an overlap is to illustrate it with a map. So when we started today, all I told you was the distance from Stein to Buell is 17 kilometers, and the distance from Niet to school was 14 kilometers. And I asked you, can you add 17 and 14 to get the distance, or is there an overlap? And all of you figured out that there was an overlap, and it was this distance from Niet to Buell. And you knew this distance was 17 and this distance was 14. So the difference is the distance between Niet and Buell. And then we use that same idea that we did with Venn diagrams. If Stein to Buell is 17, and this part from Niet to Buell is 3, from Stein to Niet must be whatever number I add to 3 to get the distance of 17 for this whole trip to Buell. So 14 and 3 is 17, just like in the Venn diagram. This is the overlapping part. And then Niet to school was 14 kilometers, but this much is already 3. So you guys all figured out 14 minus 3 gives me 11. And now I have 3 parts. I have Stein to Niet, 14, Niet to Buell, 3, and Buell to school, 11. And if I add those, I get 28 kilometers. And a lot of you also said, well, we just counted this 3 twice. So if we add 17 and 14, we get 31 kilometers. But we counted this distance twice. So we subtract one of those 3, and 31 minus 3 is 28 kilometers. So this was an example of overlap. And then I had you figure out, well, what distances could I have without the overlap? And some of you said Stein to Niet plus Niet to school. Well, so Stein to Niet could be x, and Niet to school could be y, and then I could add x plus y and get the total distance of 28. Others of you said let Stein to Buell be x and Buell to school be y, and then again x plus y is the total distance of 28 kilometers. So either one was fine. And then we talked about in class this betweenness property. So the betweenness property says if B is a location on a number line between A and C, then segment AB plus segment BC is equal to segment BAC, the whole thing. Okay, so we're just talking about this segment plus this segment equals this entire segment. And so the betweenness property literally just says that in order for me to add those, B must be between A and C. And then we also talked in class today about if I take out this little segment bar, let me just take it away, and this, take it away, and take this out from under the segment bar. And I'm going to move this equal sign here. So now I'm talking about something slightly different. Without the line segment symbol, this says the distance from A to B plus the distance from B to C is equal to the total distance from A to C. So the same idea, if I add two pieces, I get the total length of the line segment. Okay, we talked about adjacent angles. Adjacent angles are angles that are side by side. So angle PON is adjacent. This angle is adjacent to NOM because they're touching. And they share this common ray, ray ON. Notice ray ON is between ray OP and ray OM. So if I take angle PON and I add it to angle NOM, I get the total angle of the big angle POM. So again, if ray ON is between these two rays, and I'm really getting three angles here. I have angle PON, angle NOM, and then the big angle POM. And if I add the two adjacent angles, it gives me the total of this big angle, angle POM. And I can add those measures if I want. And the slide model of addition. So when I slide to the right, it's addition, and when I slide to the left, it's subtraction. And I asked you, how does this make sense when using a number line? And all of you know that on a number line, as I move to the right, the numbers get bigger. So if I'm adding something and what I'm adding is positive, it's going to get bigger and move to the right. But if I'm subtracting, taking away, my answer is going to get smaller when I move to the left. So we just acted out this problem with the slide. So Alex starts here on the 4th floor. And he takes the elevator up 5 floors. So that's 1, 2, 3, 4, 5. We slide 5 to the right, and we're on the 9th floor. He does his shopping, and then after he finishes his shopping, he goes down 10 floors. So if I slide 10 to the left, we just represented him with jumps. 1, 2, 3, 4, 5, 6, 7, 8, 9. Notice that going down 9 takes me to 0. But he goes down 10 floors. So he ends up at the floor of -1. And I said, on what floor does he end? And what's most likely on that floor? Most of you said a parking lot, maybe a parking lot, or some kind of basement. So we're just modeling with slides. So we slid to the right to add, we slide to the left to subtract, or to add a negative. So I can also write this as one big addition problem. I started at 4, I added 5, and I added a -10. So 4 plus 5 is 9, and 9 minus 10 is the same thing as 9 plus a -10. Either slide will take me to -1. So remember, the order in addition the order in subtraction matters. Notice if I have 10 and I subtract 9, which is smaller than 10, I get a +1. But if I have 9 and I subtract more than I have, I get a -1. And this is actually really easy to understand with money. So think of money. If I have $10, or if I have 10 euro, pick whatever currency you want, and I have 10 and I spend 9, I take away 9, I'm left with 1 of those euros or dollars. If I have 9 euro and I want to buy something that costs 10, well, I can pay for 9 of that item, 9 euro or $9 of the item, and then I have to borrow. I have to borrow 1 more euro to buy it because I don't have enough. So if I switch the order with subtraction, notice I get the opposite of the answer. So 1 and -1 are opposites. So you've got to really pay attention to the order. But 9 plus a -10 is the same answer as 9 minus 10. It's the same exact answer. If I have 9 and I add a -10, I slide 10 to the left. If I'm at 9 and I subtract 10, I slide 10 to the left. Either way, I end up at -1. And then we just did a lot of practice problems with. So a family owed $1,200 on a Visa credit card, and then they charged another $45. So that means they had Visa pay for that item, and they owed that money to Visa. So you wrote an addition problem to represent this. So when I have a debt, it's a negative number. So -1,200 because I owed Visa that much money, and I added to that another debt. So a debt plus a debt just makes a bigger debt. So notice I just added these two numbers and it stays negative because now they owe $1,245. And we use a negative sign to show that they owe the money. If I had a positive 1,245, it would mean that that's how much money I have. But since I've charged that much, I don't have it, I owe it. Big difference. All right, and then when we use this idea of the betweenness property, B is between A and C. So I told you that AB's length is 5 2/10 centimeters. BC's length is 11 500 centimeters. So I said, what's the length from A to C? And we reviewed about lining up your decimals. Make sure your decimals are in alignment, so you're adding tenths to tenths and hundredths to hundredths and ones to ones and tens to tens. Otherwise, your answer won't make sense. So this total distance from A to C is 16.25 centimeters, and that was illustrating the betweenness property. And then another word problem. So Jack was shoveling snow and he earned $27, but his hands were freezing afterwards. So he decided that he was going to buy a better pair of gloves. So he used 19 of the $27 to buy better gloves. And I said, what addition problem identifies how much money Jack has left? And all of you got this. You said, really, he has $27, and I'm going to add to that a debt. I'm going to add to that him owing the store where he bought the gloves $19, and 27 plus negative 19 is the same thing, $8 that I get if I just subtract 27 minus 19. Again, just getting you to see that adding a negative 19 is the same thing as 27 minus 19. So I can write this subtraction as an addition problem. I just have to add the opposite of 19, which is negative 19. And what we looked at here is, does the order in which I add numbers change the sum? And the answer is no. And that is so valuable and important that there's a special property called the commutative property of addition that simply says when I add, the order does not matter. It will not change my answer. So 17 and negative 4 is 13, and negative 4 and 17 is 13. I get the same answer. 3/10 and 25 hundredths is 55 hundredths. 25 hundredths and 3/10 is 55 hundredths. 0 and negative 7 is negative 7. Negative 7, 0 is negative 7. So the order doesn't matter. Think of the word to commute to work. So if I commute to work, that means I leave my home, I go to work, and at the end of the day, I leave my work and I go home. So whether I'm going home to work or work to home, it's the same distance. The order doesn't matter which way I'm going. It's the same distance. All right, so the commutative property of addition is important. It says the order doesn't matter. And we talked about what other properties work for commutativity and which ones are not, but we'll go into that more later. So you just had to use it to finish the statement. So A plus B equals B plus A, and x plus a negative y is equal to negative y plus x. And x plus y in brackets plus z is equal to z plus the same thing in brackets. And the slide model to show negative 3 plus 7, I start at negative 3, and I slide 7 to the right, and I end up on 4. And then you guys had to check, we did a quick checklist of your Chapter 4 blog post, which I'll be grading as soon as I finish your projects. And again, I showcased Brody's sports team project, and also you might look at Megan Black. Hers is also excellent. And I showcased Isabel's for architecture because of the way that she showed very clearly where her polygons were in the picture by drawing circles and ovals on them. And so have a look at those if you want to understand them better. And your homework practice is just both sides of the worksheet I gave you and no calculators on this sheet. This is for you to practice the computation. So if you can't squeeze it in the space given, do your computation on a separate sheet of paper and staple it to the worksheet. And that's it.